To understand how substances change phase, we need to understand the difference in some vocabulary. And first, we're going to talk about temperature and heat. Heat's a form of energy. Temperature is how we measure the kinetic energy of a substance. So remember, kinetic energy is the energy of motion. So I like to think of a temperature or a thermometer as the speedometer of our substance. So basically, you saw videos where you could see a substance moving. It could be vibrating or it could be bouncing around, and this gives us some kinetic energy, and our temperature is the measure of the average kinetic energy. So what does that mean, average? Well, if I take a cup of water, all those molecules are moving at a certain average speed. That doesn't mean that some particles aren't moving faster. Some are. That's why we have some evaporation, and some are moving a little slower. But basically, on average, we have the same temperature. And so you can think about that like the halls in the high school. If I look above during passing period, the halls are moving at basically the same speed. There are some people quickly darting in and out and going much faster, and there's some very pokey people. But in general, they're moving at an average speed, okay? So again, temperature or our thermometer is our speedometer. It measures the average kinetic energy of a substance, how fast the particles are moving. Heat, on the other hand, does have to do with the speed of those molecules plus the amount. So it's a form of energy that has to do with temperature and amount, and you watched a video that explained that very well. We have two temperature scales that you're probably familiar with. Degrees Celsius, which is the metric system. So in Europe, they measure their temperatures in Celsius. Here, degrees Fahrenheit, that's what we do. Celsius, water freezes at 0 degrees Celsius. And in Fahrenheit, here in the US, we say that water freezes at 32 degrees Fahrenheit. And here is that conversion if we want to know Fahrenheit from degrees C. And we won't be using this much. What I do want to introduce you to is another temperature scale called Kelvin. And this is directly proportional to the kinetic energy. So let me show you why Celsius and Fahrenheit are not. And this is not part of your notes. This isn't my handwriting. So remember, write everything I write on the sheet of paper. This you do not have to write. So if water freezes at 0, we know we can get colder than freezing. So we can have negative numbers here, right? Negative 10, negative 20, negative 30. And here, that's degrees Celsius. And here in the Fahrenheit scale, water freezes at 32 degrees C. But I can still get that colder, and it can go negative. Now, if this is the measure of the kinetic energy or the motion of particles, how do you get negative motion? That's very hard to define, and it doesn't work well in calculations when we move into our gas laws. So they had to come up with our Kelvin scale. At 0, that means motion ceases to exist. There is no motion. So when we use it in calculations, we won't have negative numbers for things that are colder than freezing. That's why they had to come up with it. Again, freezing is 32 degrees Fahrenheit, 0 degrees Celsius, and 273 Kelvin. So 0 is where absolute 0 is where motion ceases to exist. But it actually freezes somewhere up here, which is 273 Kelvin, and that happens to be 32 degrees on the Fahrenheit scale and 0 on the Celsius scale. Okay, so that's why we had to come up with our next form of temperature scale, which is Kelvin. It's directly proportional to kinetic energy. Absolute 0 or 0 Kelvin is where motion stops. And this conversion you will be using a lot. So Celsius plus 273 equals Kelvin. So when you get Celsius, you're just going to add 273, and you are going to get Kelvin. So looking at our phase change diagrams, we have our different phases as the temperature increases, okay, we go from a solid to a liquid to a gas as my temperature increases. And how did I get that temperature to increase? Well, I added heat energy. So as I go this way, I'm adding heat. And sometimes when I add heat, the temperature will rise. You can see when things are a solid and I add heat, the temperature goes up. When things are a liquid and I add heat, the temperature goes up. When things are a gas and I add heat, the temperature goes up. But then we have these flat parts, and notice my temperature here is at 0. Okay, that's when ice melts or freezes. And when that happens, this is a phase change. During a phase change, our temperature stays constant. And that is because we are using that energy to separate the intermolecular forces or weaken the intermolecular forces between molecules. We're not increasing temperature here. Again, when I go from a liquid to a gas or I'm vaporizing, my temperature remains constant. So I can find my phase changes by finding the flat parts on my phase change diagram. So here's my solid. Here are all my particles, all in an orderly fashion, definite shape, definite volume. And as I add heat, my temperature increases. That means they start to move faster and faster until I hit a phase change. So my solid, and I want you to think about this like water. I have this ice cube on my desk. My solid turns into a liquid as it melts. So during this phase change, the piece of ice on my desk is a solid, but a puddle is also forming. So I also have a liquid. So during a phase change, you have two phases. When I melt or freeze, I have a solid and a liquid, and my temperature stays constant until it's completely converted over to the next phase. And then as I add energy, my temperature will increase. So here I changed over completely to a liquid, and as I add that heat, the liquid molecules will keep moving faster and faster. That's why my temperature increases. Remember, that's your speedometer. Until I go from a liquid to a gas. And now my heat energy will be used to separate these particles but not increase temperature. And so let's talk about this. Vaporizing from a liquid to a gas is one type of vaporizing. It's called boiling, and that's at 100 degrees C right here. And so if you put a pot of water on and it starts boiling and you have a thermometer on there, you can crank up the heat as much as you want, and this temperature won't change at all, because during that phase change, there is no temperature change. Once it's converted completely to a gas, then that extra heat energy will increase the temperature of the gas. So just to go through this again, if I'm not changing phases, my heat energy will increase the temperature until I change a phase, and then my heat energy will be used to weaken those intermolecular forces and separate those molecules into a new phase. So remember, water freezes at 0 degrees C and it boils at 100 degrees C. During a phase change, temperature does not change. Energy is used to weaken the intermolecular forces. And during that phase change, there are two phases. You can think about that ice melting. I have a solid cube of ice plus that puddle underneath because it's melting. I have two phases. After a phase change, or when there is no phase change, energy is used to increase the motion of the substance. You can see this by an increase in temperature right here, increasing temperature, increasing temperature, increasing temperature. No temperature change, that's a phase change. No temperature change, that's a phase change.